Well, good afternoon, everybody. It's good to see so many people here live for the latest of our webinars. We have the pleasure of welcoming Dave Banks today. I'll be looking after the questions in the chat. So perhaps we can give just another couple of minutes for people to join, and then I'll hand over to Dave.
Well, I guess that means I'm ready to go. If you can't hear me, then I hope that somebody will say. My name's Dave Banks. I run a small, it's just me really, and a pot of coffee consultancy company called Holymore Consulting down in Chesterfield in Derbyshire. I also work one day a week for the University of Glasgow, but I'm not really representing them here today. I introduced this talk on the flyer with a verse from a folk song by a guy called Ewan MacColl. You can probably tell from my beard and my general appearance that I've grown up with a sort of folk music environment. And if there's one thing I've discovered, it's that there's far, far, far too many folk songs about coal mining. What I've also discovered is that folk songs about coal mining fall into two categories. The first category is songs about how horrible and inhumane and dangerous it is to work down a coal mine. And the second category of folk song is songs about how terrible it is that all the mines have closed and we don't have a coal industry anymore. So there's no pleasing some people. But I'm pleased to be able to let you know that I have found this one folk song, an example of a coal mining song that actually looks to the future. So it was written by this guy called Ewan MacColl, who's quite a big cheese in folk circles, or was. It's written in 1960. And it goes as follows, or at least the last verse does. The age of coal is ending, and the new age needs new skill. With the fuel cells and atomics, there's another world to build. And those who built the old world, their kind will build the new. For a world's not built by power alone, but by the likes of me and you. So that's Ewan MacColl writing in 1960, and it's written directly to us, to you and me, the new generation who maybe can use the old coal mines to generate new forms of energy. So this is the third in a series of webinars hosted by the Ground Source Heat Pump Association, and the series is about open loop groundwater-based heat pump systems. Today I'm going to be talking about this very, very specific kind of groundwater-based heat pump system based on the groundwater contained in mined aquifers, or mine water, as we like to call it. So I have got a PowerPoint, I'm afraid. I'm going to try and share the screen now. There we go. So I'm going to start off by trying to give you a brief history of coal mining in the UK in about 10.5 seconds. This is meant to be a slice of a coal measures aquifer. So it's sandstones and shales and siltstones with a few seams of coal. The earliest miners back in the 17th and 18th centuries, they would obviously have taken the easiest coal nearest to the surface. So they would have tunneled into the coal seam like that and taken that easy coal. And they would have found that groundwater would have flowed into those workings from the roof and the walls from the sandstones. So they would have had to drain that water away. And what they would typically have done is to drive an almost horizontal tunnel called a sough or an adit out to the nearest river. But of course, that shallow seam of coal soon disappears, and the miners would have been forced to go deeper and deeper and out to work progressively deeper seams. And now they're below the river level, so they can't rely on gravity drainage to drain the seam anymore. So they have to start pumping the water out. And that was the situation that prevailed until the 1980s and 1990s in Britain. Large, deep, multi-seam underground mines that had to be pumped out. Lots of air and water circulating, and that meant that minerals like pyrite within the strata started to oxidize and dissolve, and that little chemical reaction means that pyrite oxidizes to give acid and sulfate and dissolved iron. Acid mine drainage, in other words. What happened in the 80s and the 90s is that the mines were shut down, the pumping stopped, and the mines started to fill with water. And the water wasn't just any water, it was orange water because it contained lots of dissolved iron. And in the worst cases, that water overflowed from the mines into the local watercourses. Rather like this one that we found last week in Clackmanager. But what you're left with actually is an aquifer. It's a network of mined voids which are full of groundwater at, temperatures of 10 degrees C and upwards. But these voids aren't natural voids. They're not natural pore spaces or fractures. They're made by humans. So I think it may have been Paul Younger, I'm not sure, who coined this phrase, an anthropogenic aquifer, an aquifer made by humankind, that we can tap into and extract the water and extract the heat. Just a few words about the types of mining methodology that have been employed in the past. The oldest probably type of coal mining was what we call room and pillar or pillar and stool mining. And that was quite widely employed in the 18th and early 19th centuries. Blocks of coal being taken out by the miners, but of course they had to support the roof, so they left pillars of coal intact to support the roof. So maybe they took 40 or 50% of the coal by this means, but left 40 or 50%, 60% intact. So you end up with a network of mines maybe looking something a little bit like this. Those room and pillar workings might still be open voids, or they may have collapsed, or the miners may have been in again afterwards in a second generation, taken away the pillars and deliberately have allowed the roof to collapse. The second type of mining takes the entire coal seam along a panel. It's called longwall mining. It became common in the 19th century and was the predominant mode of mining, I guess, in the big seams in the 20th century. And in this type of mining, you have a longwall cutting machine, basically scraping out the entire thickness of coal on the left-hand side, and you have mechanical chocks supporting the roof on the right-hand side. And as the cutter progresses left and takes the coal out, the chocks mechanically walk leftwards as well and allow the entire roof to collapse behind the worked seam. This is what it looks like underground, and I was lucky enough to be in one of the last longwall faces in the deep Nottinghamshire coalfield before it closed, and it's a scary place to be and a loud place to be. You can see the cutter there on the right, the mechanical chocks on the left, and those miners could be a kilometre underground in a tunnel that is slowly moving from side to side and the roof is collapsing behind you. You don't want to think about it too much. But what you may be left with, therefore, is not an open void, but a zone of collapsed strata overlain by fractures and small voids that may be able to contain and transmit mine water and groundwater. The deeper you go, the more and more compressed these long wall faces tend to become, and it's quite possible to drill through an old long wall seam that's been worked out and not actually even know that you've been through it with a drilling machine. So the hydraulic properties of long wall mines can vary considerably, from nothing there to fractured and collapsed zones that do transmit groundwater. How do we get the water and therefore the heat out of abandoned coal mines? Well, I'm going to give you 4 different methods that may or may not work. And the first method I call pump and dispose. It's the easiest and most obvious method. You stick a pump down a mine shaft, or you drill a borehole and stick a pump down that and pump the water up. Just like any other groundwater-based heat pump system, you would then put it through a heat exchanger or a heat pump. Then you have to do something with the water afterwards. And you might say, well, let's throw it away into a river or into the sea. The trouble is, as I've already said, a lot of coal mine water tends to be contaminated with natural contaminants, sulfate, maybe salinity, dissolved iron and manganese. And typically the Environment Agency won't let you put mine water directly out into a natural recipient. So you may be left with the prospect of having to treat the mine water to get rid of some of these solutes before you're allowed to dispose of it. And that's what a mine water treatment plant looks like. That's a place called Cap House in Yorkshire. near Wakefield. This isn't specifically for extraction of heat, it's run by the Coal Authority to manage mine water levels. So instead of letting the flooded mines pop out into rivers all over the place, they have a centralised pumping shaft that they deliberately pump and treat to keep the mine water under control. But of course, the Coal Authority have realised that, well, they're not just pumping water, they're pumping heat as well. And these centralised mine water pumping stations, you know, are actually quite interesting locations to develop large-scale heating and cooling schemes around. And there are a couple of sites, most notably up in Dordon in County Durham, where the Coal Authority and its partners are doing just that at the moment. There's a really nice example of this in northern Spain, in Asturias, not far from the city of Oviedo. It's called Barredo Mine. And there they do very much the same thing as the Coal Authority do. They pump the water to control mine water levels from the mine shaft. That top left photo, you can see 4 submersible pumps going down the mine shaft. I think they pump about 200 litres a second of mine water. Then they put it through massive shell and tube heat exchangers. That's the bottom right photo, to exchange heat with the mine water, and they manage to supply heating and cooling to a major regional hospital, a university, and several other buildings. It's about 5 or 6 megawatts of installed capacity, I believe. There, the mine water quality is so good they don't actually need to treat it. So it's in many ways the ideal situation. In the UK, we're seldom as lucky as that, I'm afraid. The coal mine water quality is not so good. Second way of getting heat out of mine water, well, you can do a kind of standing column arrangement. And this has been tried by a firm called Alkane, which now are known as Infinis, I believe, who have a site near Bolsover in Derbyshire at the old Markham mine. And they've just got a little 20 kilowatt heat pump, which they use to heat their offices there. And what they've done is put a little submersible pump down the mine shaft nearby, take a couple of litres a second from quite a long way down, actually. Take the heat out of that water, then re-inject the water somewhat deeper to the same shaft, and it works. Now, obviously, you've got potential problems of feedback within that shaft. You can't take too much water or too much heat. Otherwise, you're stuck getting, you know, the cold water that's re-injected, sucked back into the pump and so on. So this kind of arrangement does work typically well with small to medium-sized schemes. There's my colleague Neil taking some samples of the water from the shaft top. You can see the flow and return pipes there. And those are shell and tube heat exchangers within the plant room. Third means of getting heat out of mine water, well, I know we're focusing on open loop systems today, but you can actually do closed loop. There are mines in Norway where they put typical heat exchange U-tubes down mine shafts and circulated a heat transfer fluid down those to extract modest amounts of heat. Or places like Cap House, where you have treatment lagoons, you can actually put the heat exchanger in the treatment lagoon and take heat out there by circulating a closed loop of heat transfer fluid around a heat exchanger. And we've done this just to prove it works. That's obviously not a U-tube, it's a plate heat exchanger that we've submerged in the treatment lagoon at Cap House. And you know, there's no great rocket science involved in this. We circulate a solution of glycol around it, and we've demonstrated that using a heat pump, we can take modest amounts of heat from that. Method 4, which is the one that most people, I guess, are considering for large-scale mine water heating and cooling schemes in the UK at the moment. It's the idea of a re-injection doublet. So in this particular case, you might drill a production well down to an open mine working, pump out water, extract or dispose of thermal energy to it, and then instead of throwing the water away, you re-inject it back to the mine workings, down an existing shaft or probably down a purpose-drilled borehole. The problem is, of course, that a lot of mine workings represent very, very open pathways, so you can get very rapid transport of the cold water from the re-injection well back to the pumping well if you're not very careful. You need long flow pathways. So rather than something like that, we're probably looking something a bit more like this. Remember that mine workings typically have many different horizons. So hopefully with a bit of thought and study of mine plans, you can site an injection well and a production well so that you don't necessarily re-inject and abstract from the same horizon, but you do make sure that there is some kind of connection there in the long term, but with a long tortuous flow pathway back from the injection well to the production well. Well, it looks simple. It's a lot easier said than done, I'm sure. I've, over the past years, been quite bullish about the possibilities that coal mines represent for thermal energy, but as time has gone on, I've learned that there are big risks and uncertainties and a lot of things that can go wrong as well. So I'm just going to list a few of those up. Mine networks have very, very uncertain hydraulic properties. Often, we may not know if shafts have been backfilled or if they've been left open, whether they represent open pathways or closed pathways. Have water dams been installed on roadways in mines? Have mine workings collapsed? If you've been down a coal mine, you know that miners pay a lot of attention to things called ventilation doors, which force air to circulate in a particular pathway around the mine workings so that the miners can breathe. It struck me that a lot of the hydraulic behaviour of mines might depend on whether ventilation doors have been left open or closed when mines have been abandoned. You know, I dream about this and worry about it a lot, but that sort of information is not recorded, and it can make a huge difference to the hydraulic properties of a mine working, I suspect. The Coal Authority has done a fantastic job of digitising and archiving mine plans, but there's always a question mark about how reliable they are. I'll come back to that. This business of getting energy from mine workings does have a very high risk profile. There's a lot of upfront uncertainty about the hydraulic behaviour of the workings, and there's a lot of upfront capital cost. Drilling investigation boreholes in mine strata and doing it properly is expensive. So you can spend a lot of money and you've got no guarantee of success. There's a tricky regulatory process. I'll come back to that as well, because you have to deal not just with the Environment Agency, but you also have to deal with the Coal Authority and Ofgem and you know all the bodies who regulate subsidies. So there's a lot of things to get lined up. And then you've got this business about the tricky water chemistry. Mine water often contains iron and manganese. It can be saline. It can contain dissolved gases. All of these can make extraction of heat tricky. Not impossible, but tricky. And because of those things, there's typically quite a large ongoing maintenance commitment. And a few of the mine water schemes in the UK that have operated for some years and then ground to a halt, it's really been this ongoing maintenance commitment that has proved difficult to overcome. So I'm just going to take a closer look at some of those risks and uncertainties. If you order a mine plan from the Coal Authority, they're very good at, you know, providing paper or digital copies, or you can go to their centre in Mansfield and look at them yourself. But they may look something like this. Not a lot of good information there. Or they may look like this, better, and probably quite accurate, but you know, what is that hatched area? How deep is it? Is it room and pillar? Is it longwall? To me, it's quite difficult to know. Or they may look like this. This is a mine plan from the 1980s. And you can see there's a lot of really, really good information there. You can see those blue dots there, spot elevations on the level of the mine seam. You can tell where the longwall panels are, where they got up to, on which particular date in 1974, and you can see the roadways. So there's a lot of really good information there. You have to ask yourself, how accurately were the mine plans surveyed? And recent plans, the answer is actually very accurately indeed. But the further back you go, I guess, the less certain you become. How accurately have you georeferenced them if you've transferred them to a GIS system? You've got to be really careful about that. And then there's this awkward question of how accurately can you drill? Well, the Swedes have done quite a bit of work on what happens to boreholes which you think are vertical. This is a selection of 21 down the hole hammer drilled boreholes to 115 meters depth at a ground source heat scheme called Emmaboda in Sweden. And those are the trajectories of the boreholes seen from above. And I think that's a 10-meter grid. And you can see that none of them are vertical. They go off in all directions. The average deviation in a 150-meter borehole was 16 meters. Now, that's one particular method in a hard rock lithology. I'm not saying it's necessarily that bad with all methods in all lithologies, but boreholes are not necessarily vertical. And if you're trying to hit a 5-meter mine roadway at 250-meter depth, I guess you can see that it's a challenge. And it's not impossible. The Coal Authority have built up a lot of experience of doing this, but you may have to have 1 or 2 stabs at it before you actually hit the target. And you have to do it carefully with the right methods and with an experienced driller. We've also found that when you start pumping mine workings, they have very unpredictable properties. This is a site I've been working on where there's several different mine seams, and we thought to start with, having looked at the mine plans, they were all interconnected and they should all behave in more or less the same way. When we came to pump them, they don't. The deep seam has a linear response when you start pumping it or re-injecting to it. The heads change more or less linearly, like a bathtub filling up. The shallow seam is completely different. The groundwater heads even out and reach an equilibrium very, very quickly. And it's probably related to the fact that they go underneath an overlying estuary. But the point is, none of these seams behaves like we expected them to. None of them behaves in a nice, polite, Theiss-like manner, which is a pumping test response that will be well known to hydrogeologists. We couldn't have known how either of those seams behaved before we started pumping. Then you've got all the difficulties with the chemistry. Mine water typically contains dissolved ferrous iron. When it comes into contact with oxygen, it oxidizes and produces an orange-brown ferric hydroxide sludge, which clogs up pipes, re-injection wells. That's a clogged re-injection well at Lungfinnans. You can see clearly that the re-injected water is coming into contact with oxygen. Big no-no. That's a clogged filter at the Coal Authority site in Dordon, a pilot scheme there. To start with, they used treated aerated mine water in their heat pump scheme and found that they got very rapid clogging of filters. When they changed the system and then used the raw unoxygenated mine water, the iron hydroxide didn't precipitate it out and they could operate the system with few problems. And that's the system at Alkane in Markham, pipes and shell and tube heat exchanger after 2.5 years operation, very little precipitation and clogging at all. That's because the water was deoxygenated and reducing to start with. So there's a lot of chemical tricks in this to get your head around if you want to minimize the maintenance requirement and the potential for clogging in a mine water system. Here's another scheme we've worked on where we used a plate heat exchanger to exchange heat between the mine water and the building heat transfer system. We found that progressively it did tend to get clogged up over the course of months by iron hydroxide, and it was found necessary to periodically flush the heat exchanger out with a weak solution of citric acid. And the photo on the left shows that flushing process. You can see all the gunk that's being washed out of the heat exchanger. Word of caution, don't use citric acid in boreholes. Oxalic acid is a better choice because the citric acid can be a food for bacteria. We've also found at several sites in the UK and on the continent that shell and tube heat exchangers tend to be a little bit less prone to clogging than plate heat exchangers do, but they're a lot bigger and possibly a bit more expensive. Now, those are all technical things. I've also often found that one of the most difficult things to get right is getting the demand correct in time and space. There's no point in having a big pumped mine water treatment scheme or borehole if it's in the middle of nowhere. You have to have somewhere to use the heating and cooling. And this particular site you can see in these photos, which is near Barnsley, always particularly irritates me when I go there, because it's one of the Coal Authority's largest mine water pumping and treating schemes. It was designed, I think, for up to 200 litres a second of mine water. In that lower photo, you can see the pump shaft. And I've watched as this housing estate of actually quite posh, nice, high quality housing has been built up around this Coal Authority pumping station. You know, there's probably 3 or 4 megawatts of heat energy going spare at that site. Did anybody want to use it? Has it been integrated into the housing? No, it hasn't. That's not the fault of the Coal Authority. It's just developers and the Coal Authority and the Environment Agency not realising the potential at the right time and not getting their act together. So timing is everything. You've got to get your demand in place at the right time and get everybody talking together, get your ducks in a row in a way. And I have to say that regulators don't make that easy, because you think you've got everything sorted out, you think you've got a client, you think you've got a source of mine water energy, but then you have to sort of go in and start talking about abstraction licenses and discharge consents with the Environment Agency. Moreover, you have to start talking about this new thing, heat access agreements with the Coal Authority. So you've actually got 2 different environmental regulators to deal with. And I have to be honest, I think both the Coal Authority and the Environment Agency are still both feeling their way with managing mine water. And it can be a long, drawn-out process. That's a word of warning for you. Well, that was a bit rambling, and I've got a lot off my chest. I really like the idea of mine water thermal energy, but I have to be honest, there are some big obstacles to overcome to get it to work efficiently.
So in the chat so far, and so just to remind you, please do type any questions you've got for Dave in the chat and I will ask them for him. Keith Parker mentions the very interesting plans of the drilling deviation, and he said that he must have experience himself that we can hit 5-metre wide roadways up to 750 metres away. Directional drilling, I guess he's talking about. Have you got any comments about, is that example you showed maybe atypical in terms of the control over and the management of the drilling?
Yeah, the Coal Authority do have experience of this, and I'm guessing Keith is talking from his Coal Authority days, and we do know that the Coal Authority have drilled many boreholes and hit really difficult targets at considerable depths. All I would say is the Coal Authority and the drillers they use do have a huge amount of experience of doing this. Don't come into it lightly. Use those drillers and those partners who do have that kind of experience to draw on. I think also it does depend on lithology and drilling method. The examples I showed from Sweden were into granite, using a down-the-hole hammer bit. I think the more, with the drilling method, the more you're trying to pull the bit down from the top of the mast, the more stress you're putting on the drill string and the more likely it is to deviate. The more you're relying on gravity at the downhole bit itself, as in conventional rotary drilling, the more likely you are to get a vertical hole and a better controlled hole. Then, of course, you've got the possibilities that directional drilling opens up. So I'm absolutely not saying it's not possible to hit those targets at great depth. All I'm saying is it's difficult. Be careful.
Yeah, absolutely. I think I would echo that, Dave. Using an experienced contractor is very important. Cheapest isn't always the best, I think is one way of putting it. So Hugh, who hosted a really interesting talk on modelling last week, has asked you to comment on the challenge of developing more numbers, that is, of designers and operators for open loop systems. Can you just comment on that?
Sorry, when you say numbers, are we talking modelling, or are we just talking about sheer quantity of schemes?
As an industry, I feel we're still some way off having the numbers of experienced designers and operators for conventional borehole open loop systems. So can you comment on how we may meet this challenge for mine water particularly?
Yeah, it's a tricky one. My personal view is that I think the Environment Agency and Coal Authority I'd love to see them get behind a limited number of demonstration projects and just do them and learn from that experience. And they are doing that. I mean, the Coal Authority is in the middle of developing a scheme in Dordon, and there are several others on the cards. But I just feel that we need to allow ourselves to try these things. And we're probably going to make mistakes, but I do think we need some really good, highly visible, well-documented demonstration projects to give, well, hopefully confidence, but at least to learn from our mistakes. And of course, like any other open loop groundwater-based schemes, we need to really draw on the experience of the hydrogeological community, integrate it with the Ground Source Heat Pump Association. In the particular case of mine work, is to draw on the experience of mining engineers and the Coal Authority in particular.
Excellent, Dave. Just to mention that the Ground Source Heat Pump Association is doing an awful lot of work currently on training, and that's from school age. We've got schemes of work for year 5 and year 7, I believe, in production at the moment and actually being trialled in schools. At the moment, we've then got work on apprenticeships right the way up to the potential for a ground loop design qualification, UK-based ground loop design qualification at more of a university level. So we're working on that very heavily at the moment. So just to mention that. Okay, so Eugene Bryce has asked, is there enough of a payoff over other heat pump types to justify the effort of getting involved with mine workings?
Yeah, it's a really good question. I don't think I've got a simple answer for him. The site I showed you in the film at the end, it's actually very shallow coal workings, 30, 50 meters deep. And they're flooded and they contain water. And the water's only 10 degrees, 11 degrees C, but I can't help feeling that you're more likely to get a return. This may be very controversial, but I do wonder, you know, with a site like that, a shallow site, you've got far less drilling risk, far less drilling costs. The drilling is simpler. Even though the temperature is lower, you can still get a, you know, really good efficiency on a heat pump based on 10 degrees C mine water. I do wonder if that represents a much lower risk profile and a better chance of getting a good capital return than trying to target 400 or 500 meter deep workings where you've got a lot of upfront risk and some very high drilling costs. I'm not saying that you know, you can't make it work. I'm just beginning to. Yeah, I just see the risk profile with the really deep schemes, and some of the shallower workings begin to look increasingly attractive, I guess is what I'm saying.
One thing I always do whenever I'm asked to look at a project in mine workings or indeed open loop is I always do a closed loop alternative and have a look at it alongside. I think that's my general approach to things. So Fiona Todd would like to know a bit more about the Clackmannanshire project, if you could.
Yeah, it's a project that is funded by the UK Research Councils. It's only a small amount of funding and it's in collaboration with Town Rock Energy. I feel that there are people who own that project more than I do. I don't know if David Townsend's somewhere in the constellation. I think I'm going to say, Fiona, have a talk with David because I don't want to steal his thunder by giving too much away. But it is at the moment, it's really just it's a site investigation to see what's down there. Rather than a full-scale development at this stage. So it's a research project based on site investigation.
Brilliant. So quick question from Philip James, should be easy to answer. How long does it take to drill, say, 150 metres, and what is the disruption like locally? Specifically, are there any seismic issues?
Well, 150 meters, it depends what you've got above. I mean, if you're just drilling through solid coal measures down to 150 meters, you know, you might do that in a day or 2 days. If you've got to go through an overlying mine working to get to that target seam, then it can take a lot longer because you might end up having to grout in a string of casing through the overlying mine working so that you don't lose circulation, so that you don't end up connecting various mine seams together. So it depends entirely on the specific situation. Fiona, having given yourself away that you're actually on the call here, you're doing your thesis on potential geotechnical issues regarding mine water extraction. I don't know, maybe you'd like to answer the question about the ground movement at seismic events. Are we able to couple Fiona in to answer that one?
I can see if Charlotte can
If she
do
wants
that.
to.
Yeah, maybe we'll see if Charlotte can do that for us. Just while we're having a look at that then, seismic issues from a closed loop drilling point of view, you bash out 150-meter boreholes in a day very, very easily with a closed loop situation, and we don't do anything like fracking or anything like that in these systems. So it's not that the same as those kind of controversial projects. So question from Jonathan, with an abstraction re-injection doublet system, is it generally the case that water is abstracted from lower down and injected higher? And what are the main design considerations?
Okay, if we're not going to get Fiona on the seismic risk, I think the short answer is I don't think there's a huge risk of ground stability with abstraction and re-injection from mine workings, as long as you're not operating at large pressures. The question of whether to abstract from lower down or higher up will be an entirely site-specific decision. You might think it's nice to abstract from lower down to take advantage of the greater temperatures at depth. My personal view is that I'd be very careful about re-injecting into shallow workings, because you might end up raising water levels in those shallow workings and lead to uncontrolled breakout of mine water. In many cases that I've looked at, I would actually prefer to abstract from the shallower workings and re-inject to the deeper ones to minimize that risk of uncontrolled breakout. But it is an entirely site-specific decision based on the mine geometry.
Okay, a couple of lovely bits of feedback from Gareth Farr and Phil Jones, both saying fantastic presentation, really fascinating. And Phil follows up with a question. Can you tell us a little bit more about the Dorden project with the mine water treatment pool approach?
Again, I'm probably not the best person to do this because this is an ongoing coal authority project. So Dorden is a mine water treatment, an active mine water treatment site on the Durham coast, where they're pumping huge quantities of regional mine water, treating it and disposing of it to the sea. Now, the coal authority some years ago decided to give this idea of taking heat from the mine water a crack, and they put in a small heat pump in the treatment centre and basically circulated mine water through a heat exchanger and demonstrated that you could extract heat from it. The first mine water they used was the treated mine water from the treatment plant, which had already been exposed to oxygen. And that exposure to oxygen meant that iron oxide precipitated out of the mine water and clogged the heat exchanger filters. They then changed the pilot scheme and used the untreated, unoxygenated mine water. So the iron didn't oxidize, didn't form ochre, and it seemed to work entirely unproblematically, I understand. The exciting thing at the moment is that having done that pilot project, they're now in the process of completely upscaling that and supplying heat to a new housing development a kilometre or so away from the treatment site. And there may be people on the call who can tell us more about that. But there's a lot of information out there on the net about the development of the Dorden site as you know, one of the first large-scale mine water residential heat supply projects in the UK.
Fantastic. So Gus Fraser Harris asks the question, if multiple schemes target the same connected mine water system, is there the appropriate legislation or regulation to determine who owns the heat resource, and what would happen if the newer scheme started to influence the older? Does the heat access agreement cover this?
Haha. Well, that's one for the coal authority. The short answer is, as far as I understand, nobody owns heat. There is no law covering ownership or access to heat at all. There might be a common law case to be brought under nuisance or something like that if that occurred. The coal authority do, however, control access to mine workings. So and that's on behalf of the Crown. So although they don't own the heat or manage the heat, they can control the development of mine water thermal schemes. And that is what I guess they're trying to do by developing these heat access agreements. I mean, I know that they're in the process of trying to think through their policy of how they're actually going to implement this at the moment. And I suspect they possibly yet haven't quite come to a firm conclusion on that, but it's pending. But the intention is, I think, with these heat access agreements that, you know, they will make every endeavour to minimise conflicts between adjacent schemes. I don't know if there's a coal authority representative who care to comment on that.
Super, Dave. Just a comment on, I'm not sure I fully understand this question from Phil Merrin, but when you answered your last question, one of the previous questions, Dave, about the shallow mine heat exchange, wouldn't it be better to access a traditional groundwater system at 10 to 12 degrees rather than expend the time and cost to go deeper in the mine to try and get higher water temperatures, I guess is what Phil's saying.
Yeah, I think if you have shallow mine workings you can access, I think that's a very reasonable viewpoint to take. If you haven't got those shallow mine workings, well, as you probably know, the coal measures in their undisturbed state aren't a particularly good aquifer. You may get 2 or 3 litres a second, you may get a bit more, but you won't get 50 litres a second from undisturbed coal measures aquifers. The question I think becomes more relevant, possibly down in Kent, where you have, you know, this huge concealed coal field overlain by a chalk aquifer. And lots of people have come to me and said, well, why don't we do this down in Kent? But then again, why would you drill, you know, a kilometre down into the coal measures in Kent when you've got a perfectly good chalk aquifer sitting on top, which is very easy to access?
And nice clean water as well.
Yeah, exactly.
Absolutely. Thanks from Malin Martin. I hope I pronounced your name right there, Malin. So thanks very much for an excellent talk, he says. And he has 2 questions. Totally agree that some demonstrator sites would be a superb way to improve confidence into technology, but what do you think the other barriers are to making this an attractive approach to heating and maybe cooling in the UK? And then where do you feel efforts are best placed in making it more attractive? That's Dan's last name, sorry about that. Sorry, yeah. It's Dan Malin Martin.
I guess I'm repeating myself a bit, but I think the main barrier is perceived risk, and I don't think it's just perceived. I think there is a genuinely problematic risk profile about large, deep mine water thermal schemes. I think that's the biggest barrier. Having also seen some of the smaller schemes operate for 10, 20 years and then fail, I think the other one is, you know, the unwillingness of clients and operators to take on this long-term sort of maintenance and constantly cleaning heat exchangers and rehabilitating reinjection wells and this kind of thing. You know, nobody wants, all they want is the heat. They want a reliable source of heat. They don't want to start engaging in hydrogeological maintenance in the long term. So I think also, you know, service companies who are willing to take on this maintenance commitment, seems to be a paucity of those at the moment. I'm not sure there's that many ground source heat pump association members, for example, who take on routine maintenance of already constructed heat pump schemes. I think a development of that sector would certainly help in giving confidence, knowing that there are firms out there who can take on this maintenance burden should it become apparent.
Excellent point, Dave. Philip James was asking if, wondering if existing mine shafts are viable and sufficiently common. Could the economics of using them be better than drilling boreholes?
I think the short answer is yes. If they exist and if they go down to the right seams, absolutely. You know, the Dordon scheme is using an existing mine shaft. Cap House has existing open mine shafts that can be used. They do exist, but the trouble is when mines are abandoned, typically we don't like leaving mine shafts open. So in the best case, they might be capped with a reinforced concrete cap, or in the worst case, they might be completely filled with goodness knows what. The Coal Authority have some records of shaft filling, but the older shafts, probably not actually. So it's a bit of an unknown quantity. But the simple answer is, yeah, if the shaft is there and it accesses flooded workings, by all means use it.
There's a very good demonstration of that. Kenza, one of our members in the Ground Source Heat Pump Association, their factory down in Cornwall is heated from a mine shaft that's on that site. It's not a coal mine, it's a tin mine, but that's heated via a closed loop simply put into the mine shaft head. So it's a good example of that. So another question, excellent presentation from Fiona Fordyce. Thank you, Dave. As you say, more demonstrator sites will raise our understanding and design efficiency of design of the technology. Sorry, so it's agreeing with you there. And thanks, Dave. Any good papers or references which explain in more detail the practical setup of pipework pumping treatment for managing water chemistry and dissolved gas for re-injection? That's from Peter McAvoy.
Yeah, there are. Whether they're all in the same paper is another question. I can certainly try and put together a little list of key papers, which I can pass on to you, Chris, for sharing afterwards.
That'd be super. Charlotte, could you make a note that Peter McAvoy would like to receive that particularly, and perhaps we can make some available on the Groundwater Heat Pump Association website or links to the appropriate place.
Yeah, absolutely.
That's the last of the questions that have been posted. So that's been a fantastic response today. You've been very popular, Dave, so that's excellent. So I guess it just remains for me to say thank you very much indeed for your time and for your
welcome
presentation together.
Yeah, no, you're welcome. Thanks for listening.
My pleasure. Now, next week, we're going to have John Findlay talking about open loop water wells. So this is from the aquifers that Dave was talking about in Kent, for example. There's many around the country. And then I'm afraid you're stuck with me in a fortnight's time. I'll be trying to pull all the threads of this together and talk about what happens when we get out of the ground and into the plant room with open loop projects. So thank you very much indeed again to Dave. And we very much look forward to seeing you at the next few presentations.